In November 1890, a financial panic was closing in on George Westinghouse, and his lenders had found the one contract clause that could sink him. It was a staggering per-horsepower royalty owed to his eccentric star inventor, Nikola Tesla. The bankers demanded Westinghouse cancel the royalty or face liquidation. I'm going to show you how the most important motor ever built forced its inventor to give up a fortune to save it, and why this mechanically perfect machine can only produce power while it is losing a race against itself. To understand why a man would willingly walk away from a contract that on paper could have made him history's first billionaire, picture a pristine copper-wound stator of an 1888 Tesla induction motor glowing under a single hard spotlight against the dark. That ring of copper was Tesla's masterpiece, and in 1890, it was in danger of taking down the only company brave enough to build it. 2 years earlier, Westinghouse had licensed Tesla's AC patents for $60,000, plus a royalty of $2.50 for every AC horsepower generated. It was a spectacular deal for Tesla. But as the panic of 1890 dried up credit across the country, Westinghouse's backers issued an ultimatum. The AC grid was expanding too fast, and the royalty would soon bleed the company dry. By early 1891, Westinghouse went to Tesla and laid out the brutal math. If the royalty stayed, the lenders would pull their funding, Westinghouse Electric would go under, and the alternating current revolution would die with it. Tesla had a choice. He could hold on to a legally binding contract that promised unimaginable wealth, or he could let it go to ensure his motor actually made it into the world. He chose the motor. As the story goes, he dramatically tore the contract to pieces right there in the office. While that theatrical staging is likely an embellished legend, the underlying financial sacrifice is a heavily documented historical fact. Tesla released Westinghouse from the royalty. He gave up his empire to keep his magnetic field spinning. But what made this specific motor worth sacrificing an empire for? To answer that, we have to go back to 1882. Tesla was a young engineer in Budapest. Born in 1856 in the Austrian Empire, he had survived a brutal bout of cholera in his youth. By his own later account, that illness was what convinced his father to let him study engineering instead of joining the priesthood. Now, he was working for the Budapest Telephone Exchange, and he was obsessing over a fundamental flaw in electrical engineering. At the time, every practical motor in the world relied on a mechanism called a commutator. It was a spinning cylinder with spring-loaded carbon brushes that physically rubbed against it to reverse the electrical current twice per revolution. Those brushes were a nightmare. They sparked, they wore out, they required constant maintenance, and they were a massive fire hazard in dusty factories. Tesla wanted a motor with no brushes, no sparking contacts. Tesla later recalled the moment it broke open, walking in a park at sunset with a friend, reciting poetry, when the answer arrived whole. What if you didn't switch the current mechanically? What if you made the magnetic field itself rotate? As he told it, he grabbed a stick and sketched the diagram in the dirt. If you place sets of coils in a circle and feed them alternating currents that are phase-shifted, meaning their electrical waves peak slightly out of step with one another, the combined magnetic field doesn't just pulse in place, it sweeps around the circles smoothly at a constant speed dictated by the frequency of the current. It was a brilliant, invisible tornado of magnetic force, and Tesla was not alone in seeing it. The Italian physicist Galileo Ferraris had independently demonstrated the same principle by 1885 and published it 2 months before Tesla's patent was granted. But Ferraris gave the idea away to the scientific community and never patented it. It was Tesla who secured the foundational patents and partnered with Westinghouse to turn the principle into an industry. The rotating magnetic field was the conceptual breakthrough, but a field is just a ghost. To do real work, it needed a physical rotor to push, and that is where Tesla's design achieved a level of mechanical elegance that borders on magic. In May 1888, Tesla was granted U.S. Patent 381968. It detailed the polyphase alternating current motor. The outside of the motor, the stator, houses the fixed coils that generate the rotating magnetic field, but the inside, the rotor, is what makes the invention a masterpiece. Engineers call it the squirrel cage. It is essentially a cylinder made of steel laminations with thick aluminum or copper bars embedded around its surface. These bars are short-circuited at both ends by heavy conductive rings. Here is the crucial detail. The squirrel cage has absolutely no electrical connection to the outside world. There are no wires touching it, no brushes, no commutator. It is a completely isolated chunk of metal spinning freely on a shaft. So how does electricity get into it to create the magnetic force needed to turn the shaft? It doesn't get pushed in, it gets induced. When you turn the motor on, the stator's rotating magnetic field sweeps past the stationary metal bars of the squirrel cage. According to Faraday's law of induction, when a magnetic field moves across a conductor, it induces an electrical current inside that conductor. Suddenly, those isolated copper bars are surging with electrical current, and because they are now carrying a current inside a magnetic field, they experience a physical push, the Lorentz force. The rotor is dragged into motion, chasing the rotating magnetic field around the circle. It is a motor that powers itself across an air gap, using nothing but the geometry of invisible fields. Spark-free, sealed, cheap to mass produce. It is the workhorse of modern industry. But this mechanical perfection hides a fatalistic catch. The induction motor is a marvel, but it is bound by a strict rule of physics. It can never actually win the race it's running. Imagine the rotating magnetic field is spinning at exactly 3,600 revolutions per minute. The rotor is being dragged along behind it, accelerating faster and faster. But what happens if the rotor actually catches up? What if it reaches perfect synchronization and spins at exactly 3,600 RPM alongside the magnetic field? If the rotor and the field are moving at the exact same speed, the relative motion between them drops to zero. The magnetic field is no longer sweeping past the copper bars, it is just sitting stationary relative to them. And Faraday's law is unforgiving. It requires a changing magnetic environment to induce a current. If the relative motion stops, the induced current instantly dies. If the current dies, the magnetic pushing force vanishes. The torque drops to zero. The motor stops driving the load. To survive, the rotor must never catch the field. It must always lag slightly. Engineers call this rotational lag slip. Under normal load, a squirrel cage rotor spins about 1 to 6% slower than the magnetic field. That slip is the only thing keeping the motor alive. Nothing rubs and nothing touches. It is the field sweeping past the slightly slower bars that keeps the current and the force alive. The most important motor in history only works while it is losing. For over a century, slip was simply an accepted reality, but engineers eventually found a way to survive perfect synchronization. If a synchronized rotor loses its induced current, the solution is to stop relying on induction. Instead of a squirrel cage, modern engineers built rotors packed with powerful permanent magnets. Because the rotor carries its own permanent magnetic field, it doesn't need the stator's sweeping motion to induce one. It simply locks its own magnetic poles into step with the stator's rotating field, and the two spin together in perfect harmony. This is the permanent magnet synchronous motor. It has zero slip. And this brings us to an incredible modern irony. When the car company that took his name put its first vehicles on the road, they powered them with alternating current induction motors, the direct descendants of Nikola Tesla's 1888 patent. The slip mechanism drove the early Model S. But as electric vehicles evolved and demanded even higher efficiency and range, the industry began to shift. Many of today's electric vehicles, including newer Teslas, run on the slip-free Synchronous design instead. They still use his rotating magnetic field, but they swapped out his ingenious squirrel cage for permanent magnets. The company named after him now relies heavily on a motor that outgrew his most beautiful constraint. Tesla's alternating current system went on to conquer the world. In 1893, Westinghouse used it to brilliantly illuminate the Chicago World's Fair. By 1895, they had built the colossal Adams power plant at Niagara Falls, and within a year, it was proving that AC could generate immense power and transmit it over 20 miles to Buffalo using high-voltage transformers. Direct current couldn't do that. Tesla had won the war of the currents. But Tesla's mind was always racing ahead to the next impossible thing, and it eventually outran reality. In 1901, backed by J.P. Morgan, he began building Wardenclyffe Tower on Long Island. Tesla's radio tuning patents were brilliant. They eventually formed the basis of early wireless communication. But at Wardenclyffe, he overreached. He believed he could use the Earth itself to transmit not just information, but industrial electrical power globally with zero wires. It did not work, and the reasons why are a story of their own. What sank the tower first was money. Morgan had already refused to put in another dollar, and when Guglielmo Marconi sent a simple, cheap wireless telegraph signal across the Atlantic, investor confidence in Tesla's massive, expensive tower evaporated. The project collapsed, and the tower was eventually dynamited for scrap. Tesla spent his final decades drifting through New York City hotels, proposing grandiose inventions that never materialized. He had released a royalty that, on paper, could have made him one of the wealthiest men in human history, all to ensure his induction motors survived. And there is a quiet trap inside that arithmetic. The contract was only ever worth a fortune in the world where he surrendered it. Had he held on, the lenders would have taken Westinghouse, the grid would have stalled, and a royalty on horsepower nobody was generating would have been worth precisely nothing. The motor survived, the AC grids survived, but on January 7, 1943, Nikola Tesla died alone in room 3327 of the Hotel New Yorker, leaving behind an estate that was essentially worthless. Today, his ashes sit inside a gold-plated sphere in a museum in Belgrade. And every time a doctor powers up a modern MRI machine, its magnetic strength is measured in a unit adopted by the world in 1960. They measure it in Teslas. Nikola Tesla engineered the modern world, but he was ultimately consumed by his refusal to compromise with the limits of physics and finance. He built a motor that powered itself by endlessly chasing a goal it could never reach, a perfect metaphor for his own life. What do you think is the most tragic part of Tesla's story? The fortune he gave away, or the impossible wireless dream he couldn't let go of? Let me know down in the comments. If you enjoyed this video, induce a current in that like button and subscribe to LynxSifts Tech and Science so you never slip behind on our latest stories. I'll see you in the next one.